In this video, I introduce from deep neural networks to world models. Artificial neural networks are motivated by the observation that human intelligence emerges from highly parallel networks of relatively simple nonlinear neurons that learn by adjusting the strength of their connections, which can learn internal representations for different tasks such as object classification and neural language understanding as shown here. This input and this output. Stochastic gradient is applied to measure the connections strength between neurons through backpropagation, as shown here. It has been proved that a deep neural network is powerful when it's trained on a large-scale dataset. Deeper neural networks generalize better for the kind of input-output relationships since they exploit a particular form of compositionality in which features in one layer are combined in many different ways to create the more abstract features in the next layer, as shown here. The elements in the deep layers contain more abstract features than the elements in the shallow layers. Also, rectified linear units and residual connection are used to improve deep neural network or training. The deep neural networks are still hard to train due to large training dataset and a large number of model parameters. One of the most effective solutions is to use unlabeled data to pre-train the deep neural networks on large unlabeled dataset, and then use a small amount of labeled data to train actual layers. As shown here, this ReLU nonlinear activation function, and this residual block. The breakthrough in deep neural network architectures is a transformer that uses query key value vectors to construct a syncing memory by which the output can pay attention on the relevant elements in the input without considering the order in the input. This is the architecture of a transformer without using convolution operations. This ReLU used in feed-forward block and this residual blocks. When reinforcement learning is based only on real words, it requires a very large number of interactions. This learning method tends to produce task-specified specialized systems that are often brittle outside of the narrow domain they have been trained on. Humans are able to learn massive amounts of background knowledge about the world, largely by observation in a task-independent manner. This knowledge underpins common sense and allows humans to learn complex tasks, such as driving, with just a few hours of practice. World models use a pre-trained encoder to deeply understand the world by predicting the missing regions in an image or words in a sentence in a self-supervised manner, such that the predictor can use a small amount of labeled examples to train the predictor to produce the optimal policy, as shown here. This is a world model, this predictor, and this encoder. World models use the contractive learning to predict the possible future states by learning the latent representations of the continuous state instead of physical state in the original domain. For more details, please check with these references. Thank you. Bye.